The purpose of this presentation is to explore the ideas of successive ionisation energies and what information can be gleaned about the atomic structure from those values. First of all, let's try to define the term second ionisation energy. So we can use an equation for this if we wish, and this is the amount of energy needed to remove 1 mole of electrons from 1 mole of gaseous ions with +1 charge to produce 1 mole of gaseous ions with 2+ charge. The first feature about second ionisation energy is that it is always higher than the first ionisation energy for a particular atom. So let's consider why that is the case. So let's look at magnesium as an example. So here is an example of a magnesium atom, Mg. Its electron arrangement to H2 because there are 12 electrons in total. And here there's the nucleus with 12 protons in that nucleus. If we remove 1 mole of electrons from 1 mole of those gaseous atoms, we produce 1 mole of Mg plus ions. Each of these has electron arrangement 2,8,1, and there are now only 11 electrons, even though there are a total of 12 protons here. So that to there would be the first ionisation energy, and 1 mole of electrons would be removed. This one in this example diagram. So the second ionisation energy then would produce the Mg2+ ion over here, Mg2+. That has got electron arrangement 2,8. There's now only 10 electrons. Again, 12 protons in that nucleus. This represents the second ionisation energy. And again, 1 mole of electrons being removed, in this case, this one from the outer shell, like so. So if we consider the difference between that first ionisation energy and the second ionisation energy, in the first ionisation energy, we've got 12 electrons in the atom altogether, and the outermost electron here is in the third shell and being removed from that third shell. In the second ionisation energy, similarly, this outer shell electron is in the third shell and is being removed, but in this case, we've got a total of 12 protons attracting only 11 electrons. And that causes all of those electrons to be attracted more strongly towards that nucleus, and the electrons move a little closer to that nucleus, so the ionic radius of Mg plus is smaller than the atomic radius of Mg. Therefore, it takes more energy to remove that outermost electron from Mg plus than it does for the outermost electron in Mg. And indeed, that would hold for all of the atoms. The second ionisation energy then produces this substance here, and interestingly, if we wish to remove any more electrons, the next electron would have to come from the second shell. So one would expect the third ionisation energy of magnesium to be much higher than the second ionisation energy, partly because that would then involve 12 protons attracting just 10 electrons this time, so that would cause those 10 electrons to attract more strongly and a little closer to that nucleus, but mainly because we've lost a shell. So the third electron is coming from the second shell, which is much closer to the nucleus and less shielded from that nucleus than that third shell was. We can use this idea of successive ionisation energies then to help us to work out which group a particular atom falls in. In this case, removing the first electron, then the second electron would involve an increase in ionisation energies, but then we'd expect a big increase up to Mg2+. Similarly, let's have a look at this particular example here. So we've got another example just here. Again, the first electron and the second electron, there's an increase in ionisation energy, but not a huge one. And then there's here a big step up. So this big step up is in order to remove a third electron. So that implies that the outer shell electrons, which had increasing ionisation energy from number 1 to number 2, from the first to the second ionisation energy, but then a big step up to the next one. This suggests a new shell. So the big step up suggests the new shell. And therefore this example had 2 outer shell electrons, therefore we'd expect it to be in group 2, and indeed this is in group 2. This is the successive ionisation energy data for beryllium as on your sheets. So to summarise, successive ionisation energies always get higher, but sometimes they get much higher, which suggests a new shell has been entered for the removal of the next electron.